I've been working in artificial intelligence and teaching research and practice now for about 45 years. So I've seen a lot come and go. I've seen ups and downs. I've seen overall a kind of steady drumbeat of success. In fact, often disruptive success, and I'll get more on that in a minute. So my question is, that I'd like to address in this talk is, why now? Why are we now seeing this kind of hockey stick uptick in the success of AI deployments, at least what I see in the commercial sector? So of course, there's factors like Moore's Law and factors like the increased availability of data. Those are definitely important factors. But from my perspective, those raise all the boats. What is it that's unique about where we are right now in artificial intelligence that's caused this outsized uptick in success? So that's what I've been puzzled about, and let me give you my best guess. So first, what is artificial intelligence? Well, it started in 1956 with the audacious goal of trying to understand human cognition so well that you can endow a computer with those capabilities. And the AI community studied the inventory of AI, of cognitive abilities, pretty much by that timeline, starting with understanding what does it mean to know something? How would you build an artificial memory of knowing things? Reasoning, natural language processing, more recently machine learning and computer vision, and now we're on the cusp of robotics. That's the inventory of human cognition. Over the course of this history, and certainly in my career, I've seen these disruptions. I've seen, for example, how AI is now the winner at all the hard games, including Go, which people never thought would succumb. Route finding, we all use Google Maps. That's an AI technology from the early days. Marketing and commerce gave us e-commerce. It gave us Google Words and so on, Google Ads. Search that we all use every day, Google for information retrieval. More recently, Watson, which was considerably more sophisticated and capable, but did require heavy compute, so hasn't really broken out into common use. Natural language processing. Today, machine translation, one of the tasks in NLP. Machine translation is a solved problem. Real-time translating telephone. You know, one person talks English and another person hears Chinese. They have a conversation in real time. That's been solved now for about 5 years. You can buy a device for about $500 that will solve that across 40 or so languages. Computer monitoring. For example, a piece of equipment. We saw an example of that in our demos today. Monitoring equipment, looking for abnormal behavior and future failures. Surveillance, like you do with computer vision. These are now disruptive technologies that are changing the way that these problems have been addressed before AI. Generative AI and ChatGPT, I don't even know where that's going to go. Who knows? But it's going to be disruptive. And it's in addition to everything else we've seen. I think drug discovery and autonomous vehicles are going to be soon on our heels, but we're not there yet. So think of another technology that's had this impact on the world. I can't think of any. Maybe a technology is successful if it disrupts one industry. Look at where we are. Why? Why is AI having this outsized impact? And why is the cadence of success picking up so significantly, not only in frequency, but in amplitude, in impact, in size of the impact? Why? OK, well, let's look at AI from 30,000 feet. Here's the kind of problems that are solved by AI. And there's a lot of bubbles here that I haven't put words into, but there's a lot of bubbles in this space. You saw demos today. We've heard about some of these that I have put words into the bubbles. These don't have a whole lot in common with one another. Why would computer vision and language translation and cybersecurity, why are they all being solved by the same technology? Well, let's look at these technologies. Technologies like knowledge graphs and rule-based systems that were in the history of AI and to some extent are still with us. But what's really having an impact of late is machine learning. The idea with machine learning is simply this. The AI community, in fact, no humans, know how to write the computer program to automate most of human cognition. It's just unknown and undoable and too hard. We spent decades trying to write a parser for a natural language, like in English or Russian. Couldn't figure out the parser. Decades went into that. Hundreds of people's lives went into that problem. The idea with machine learning is don't try to write those programs. We don't know how to. Let's instead write a machine learning program and give it lots of examples of correct behavior, and let the machine learning program infer what that algorithm must be. And that's turned out to be very successful. There's one technology in particular for machine learning called neural networks that I'll talk a little bit more about, and you probably already know. And there's a subset of that called deep learning, which sounds really fancy and whatnot, but all that really means is a neural net that has more than 2 hidden layers in it. It's a little bit complex neural net, but not significantly so. So deep learning is just a category of neural nets, which is a category of machine learning. But this is the thing that's really hit home runs of late. So AI, why now? I think what we've seen is that the problems that AI can solve well have been growing significantly, especially in recent years, because of 2 forces. By one force, we're finding ways, or machine learning, deep learning, has exhibited a capability of building a solution to one problem as a kind of foundational solution, and then incrementally building, bootstrapping, scaffolding, more complex solutions on top of that, solving harder and harder problems given an initial germ of a simple problem. It's what we all do as humans, right? We learn basic knowledge in first grade, that builds on second grade, and so on, and pretty soon you have a domain expert. That's working in machine learning, and it hasn't worked before. This is a new development in the field, is that we've figured out how to do this scaffolding of capabilities. So that's one force. The second force is causing this breadth. You know, on the previous slide, I talked about how, look at those things in the bubbles, problems that are solved by AI, cybersecurity, computer vision, machine translation. These seem to have nothing to do with one another. Why would one technology solve them all? It's this breadth of coverage is what we're experiencing. What we found, what we maybe have stumbled into, is this algorithm of deep learning that surprisingly has this breadth of coverage. The same algorithm solves multiple problems in multiple verticals, problems that you think have nothing to do with one another. Okay, so why now? So first, the scaffolding of capabilities. Next slide. I want to illustrate this. In fact, I want to illustrate both of these points with products from Spark Cognition or technologies you've seen here today. So computer vision. Computer vision starts with what's called a foundational model, an initial starting point, the first grade level of knowledge. In the case of computer vision, it's training a model to recognize in a scene, in a snapshot, one object, a piece of furniture, a piece of food, a dog or a cat. That's the foundational model. Single object detection and identification. And that dates back to pretty much the beginning of this huge data set called ImageNet that was used to train this first grade level of computer vision. Now that enabled scaffolding, and we've seen it in our product. It enabled, for example, to build on a computer vision model that's able to do in-context object detection and to do that for multiple objects in the scene. So this is an example of it. There's multiple cars and trucks and people and traffic lights and all that stuff going on in this scene, and they're all recognized by one model. Why? Because that model was started with, bootstrapped from the first grade model. And that's enabled the next generation. We can also do not just recognizing the objects in a scene, but also recognizing situations. So for example, in this scene, one situation is that the crosswalk is unblocked for legal crossing. Why? Because the traffic light's in your favor, There's no cars blocking the crosswalk, so you're good to go. So that's kind of situational awareness that comes from not only being able to recognize the objects, but to do some reasoning on top of it and to put A and B together to draw a conclusion. Situation identification. That's also enabled activity recognition. And activity is something that can't be recognized from a snapshot, a single image. It takes a sequence of images, a video, to be able to recognize an activity. So for example, one activity here is jaywalking, walking outside of the crosswalk. Maybe you could do that from a single image, but all you really see here is a person standing in the road. It's not necessarily jaywalking. We have this in the computer vision product sold to retail stores to recognize shoplifting. What is shoplifting? It's picking up something in the store and exiting the store without going to the cashier. Takes a sequence. It's all scaffolding off of the models before. Here's one that we're building up to. It's done in research labs today, and it will soon be in the product. Image search and querying. So you have a corpus of maybe 3 months or maybe 3 years of image history, video history. Could you query that like you do a Google search? Can you find a man dressed in black jaywalking on a city street? Okay, here it is. Prompts, queries, post in natural language. And where I think this is going next, and again, it's in research labs today, super resolution and augmented reality. So one of the cars in that previous scene is this taxi, but in that scene, the cityscape scene, most of this rear end of the taxi was occluded. Okay? Using AI, we can fill in those blanks. In fact, the technology that we're working with at Spark right now can take an image of your face, occlude, cover up 99% of the pixels, and with the remaining 1%, reconstruct your face. Now, I get to choose which 1%. The AI gets to choose which 1%. So, in summary, what we saw here as an important development in AI is the discovery for the first time in my experience of this ability to build complicated capability by scaffolding from simpler capabilities. We're seeing transfer of capability across models, and we had not seen that before. The second reason why I think we're seeing this significant uptick in AI success is that general purpose deep learning is working across domains. Let me tell you what I mean by that. Next slide. First, what are neural nets? What is deep learning? Neural nets are just a digital twin of a human brain. It's inspired by the human brain. So if you look at the visual cortex part of the human brain, this might be a slice of it here. It takes as input visual images from your retina, and it produces as output identified objects. That's what the visual cortex does. Like the rest of your brain, the visual cortex consists of axons and dendrites. Axons are where this kind of computation takes place in a neuron. I've circled one in red. And then these dendrites are these connective tissue that reach out from one neuron to the next neuron to the next neuron. They form these neuron chains. What we've done with neural nets is to build a kind of digital twin, but don't write a whole lot into that phrase. The analogy is not that strong. Okay, what we've done is to simulate that in software so that the data structure, called a neural net, and here's a node in it that simulates an axon, and it has connections to axons further down the road by way of these dendrites. Okay, so we built these neural nets, been doing it now for 40 years. What they enable you to do, here's a neural net, a little bit larger one, still minuscule by how these things really are. But nevertheless, a neural net, you see it takes as input, let's say this neural net's been trained to do face recognition. It's going to take as input this guy's face, and it's going to produce as output the name that goes with the face. That's how face recognition models are built. What we're going to take as input is every pixel of this picture. So here's a little patch of his face, just enough that I could fit on the slide. But we're sampling every pixel of the picture. And we're going to push that through this neural net. And the neural net is going to do computation by taking the energy levels of each pixel into these input nodes, pushing it through this network of dendrites, and on every connection, there's going to be a weight applied. So at the end of the day, there's a weighted computation that comes out the back end. All 4 of these nodes will be activated to some degree, will have some quantity in them to some degree, and the one that's highest rated is the winner. So that's how neural nets work. And there's a single algorithm called deep learning that is able to train these neural nets to figure out what weight should go on every arc, every connection, so as to maximize the probability of success. And you train this neural net by taking in billions of pictures of people, including Tom, labeled pictures, and adjusting these weights so as to maximize performance on that training set. That algorithm and this basic idea of deep learning works over and over again. You turn a crank. Here we have a neural net that's going to solve a different problem. This one is for maintenance log information extraction. You saw it as one of your demos today. This time the input is going to be text coming out of a maintenance log, feeds into, here's 1 pixel at a time if you like, 1 word at a time in this case. That energy passes through this network and comes out the other end. One of these nodes will be the most highly activated, or in this case, they're all going to be sufficiently activated to produce this summary of the maintenance log information. Okay? But it's the same basic architecture, the same basic algorithm is used to solve this problem too. Next slide. Here we're going to do the same thing, this time for detecting abnormalities in this combustion turbine. This time the sensors, and there might be about 500 of them in a device like this, sensors are putting values into the neural net, and what comes out the other end of the computation this time is a measure of the degree to which that collection of sensor values is deviating from normal. Same algorithm, same approach to training it. Last one I'll do. This one is on cybersecurity, endpoint protection. You saw this as one of your demos. This time we're going to sample as input, either an information packet or a file reaching an endpoint. And we're going to draw information, maybe word at a time, bit at a time, byte at a time, as you like. Draw that out of this input, feed it through the network, and what comes out the back end is it's not malware, it's virus, it's a Trojan, it's a keylogger. We'll see. Same general approach. Works over and over, turning a crank. Now, data scientists in the room are going to say, wait. I spend my days and weeks tuning these applications. I get it. I know you do. Good job. Okay. But you've got to admit, you have to admit that it's a striking realization, right? That this Swiss Army knife of algorithms here is solving end-to-end problems, generating complete solutions, solving an end-to-end problem. The same algorithm is doing all these domains with just a little bit of tweaking by this one data scientist. That is amazing. And it's one of the reasons why machine learning is working now to such a startling degree. Next slide. And that's before we get to generative AI. ChatGPT is rewriting the storyline. I have queried my colleagues. No one saw it coming. I didn't see it coming. There's a hockey stick move here that has disrupted everything to the degree where nobody could have predicted what we're seeing today. We're not even sure what it is that we're seeing today. That's why you saw thousands of the AI scientists saying, whoa, let's stop for 6 months. You know what? 6 months from now, we won't know any more than we do today. Just be aware of this division here. There's generative AI like you're seeing in ChatGPT. There's Midjourney that does the same kind of thing, but for images. And there's other models as well. And that's the new kind of kid on the block as far as what the public is seeing, at least. And before that, what we saw, and all of the examples I presented in the earlier slides, are on the other class of AI models called discriminative. So these 2 general classes. This class is going to take off in importance, no doubt about it. What we're doing at Spark Cognition with generative AI are these three things currently. We found a way using generative AI and the Midjourney style, the kind that's generating pictures, to accelerate seismic imaging for a large super major oil company that we've been working with for 2 years now. And we can accelerate seismic imaging by 30x. This is a game changer for their industry. Second, we've been using generative methods to access maintenance logs, work orders, and technical manuals through chat. So it enables users to say, for example, maybe you're operating wind turbines. Tell me how production's been on turbines 12 through 15 for the last 6 weeks. Or turbine 7 needs oil change. Look it up in the OEM manual. So you get you get various successful chat dialogues out of this technology pretty much effortlessly. And we've also found it's very good at automating programming. So, it's not just automating simple programs, it's automating esoteric program writing as well. Now, to avoid leaking customer data, we always start with open source LLMs. And then we fine-tune them on-prem. So the customer receives fine-tuned to their domain LLMs that they can trust are not leaking their data. So that's a brief history of AI. I hope it's shed some light. It has for me, just developing the talk on why we're seeing this sudden uptick. Thank you very much.